Hello, everybody. My name is Zach, and I'm a physical geographer, geomorphologist, and educator. Welcome to Bite-Sized Geomorphology, a series of short lectures designed to teach introductory topics in the fields of geomorphology and physical geography. In this video, we're going to be talking about some of the common ratios that we use in fluvial geomorphology, how they're calculated, and what they mean. So let's go ahead and dive in. Let's think back to middle school. Now, aside from a plethora of extracurriculars, awkward experiences, and likely quite a bit of homework, you probably learned about ratios. To refresh, a ratio is simply the comparison of two values as a quotient. Typically, we'll reduce this fraction down to better simplify our results. For example, using a classic, I have 8 apples, and I've got 4 bananas. And aside from the potential for a really awesome smoothie, my ratio of apples to bananas is 8 to 4. Simplified down, that's a 2-to-1 ratio. For every 2 apples, I have 1 banana. Now, in geomorphology and physical geography, we don't really care about apples and bananas unless in case we need a snack in the field or they're growing on a really cool landform. However, we do have similar ratios that help us describe geomorphic features. You've probably seen these evenly spaced linear features along a beach or on a dune or in a stream or a river. These are called ripples, and they often form as the result of a fluid, whether that be air or water, flowing over a sandy surface. A standard ratio used to describe ripples compares the length between ripple crests, seen here, to the height of the ripples, and is known simply as the ripple index. This ratio allows us to compare ripples wherever they may be found. Now, typically, this ratio ranges between 15 and 20. 15 to 20 what? Well, in this case, we're comparing two length terms, so the units will cancel out and the ratio is unitless. And it should also be noted that things like wind speed, grain size, or moisture can alter that 15 to 20 ratio, so it's not perfect. But ratios allow us to generalize relationships between variables so that we can compare them across time and space. In the case of these wind ripples, such established relationships can tell us a lot about the processes that formed them, such as the direction of the wind at the time or the approximate speed of the wind, which can be really informative if we don't have access to things like recent meteorological data. Now, let's talk about a word you're going to hear a lot in the upcoming slides: Bankfull. When talking about stream or river, Bankfull stage refers to a frequently occurring stage of water that represents the initial point or incipient point of flooding. Think of it as the boundary between no flooding happening at all, where water is contained solely by the channel, and the initial stages of flooding, somewhere between here and here. Now, these two pictures are examples of the Chippewa River in the city of Eau Claire, Wisconsin, in the United States before and during flooding. And oftentimes, we associate Bankfull stream discharges occurring roughly every 1.5 years. Bankfull has come to be an important topic, particularly in stream classification and the parameterization and measuring of different aspects of a river. Some very prominent stream classification methods, such as the Rosgen stream classification system, use Bankfull to calculate different ratios that can be compared to rivers across the world. So let's use this cross-section as an example to show you where the Bankfull stage could be. Now, perhaps during low flow, the river stage occupies about this much of the channel, and it's not anywhere near flooding stages. Now, Bankfull would be right about here, where the top of this ridge would signify where the Bankfull stage would get to. Anything above that is considered actively flooding. Now, a ratio that is based on the Bankfull stage, the width to depth ratio, is the first one we're going to talk about in this video. The width to depth ratio essentially is used to describe the shape of the channel, where the maximum width of the channel at the Bankfull stage is compared to the average depth of the channel at the Bankfull stage. Now, the easiest way to think about this ratio is that large ratios are going to correspond to wide and shallow channels. Now, remember that in this case, the width is the numerator. So large widths without equally large depths are going to result in high values. On the other side of that, small ratios will then correspond to narrow and deep, likely incised channels. Now, in a previous video, we discussed the longitudinal profile of a river and how the cross-sections tends to evolve in the downstream direction. Looking back at that diagram, we could expect that the lowest width to depth ratios will be higher up in the stream, where the stream is usually actively incising, there's not as much water flowing through the channel, and it's generally more confined by its walls. The highest numbers on the other side will be down on the right side of this diagram near the base level of the stream, where it's moving around laterally, it's depositing sediment, and it's not really incising. So thinking about it in this way, we can use the outcomes of these ratios to approximate the type of channel we're examining. And if we do this at multiple stages along the river, we can start to get a good idea and characterize how the width to depth ratio changes along the course of that stream. The next ratio we'll discuss, the entrenchment ratio, was defined by Rosgen in 1994 as the vertical containment or confinement of a river. Now, this ratio was developed by Rosgen as a way to provide a consistent benchmark to measure and compare the extent of incision across streams, which can help us understand whether a stream is actively incising or maintaining a more stable state. We will think of the entrenchment ratio in a similar manner to how we discuss the width to depth ratio. However, rather than the Bankfull or the width of Bankfull discharge against the average Bankfull depth, the entrenchment ratio is driven by the width of the flood-prone area. The width of the flood-prone area is measured at a depth that is twice that of the depth of the maximum Bankfull depth. Seen here, and that's a lot of words, but let's just take a second to take this diagram in. So we'll divide the width of that flood-prone area by the Bankfull width that we talked about before. Now, looking back at this diagram from Rosgen, we can think of this ratio as a proxy for how regularly the land adjacent to the channel is inundated with water, where the slightly entrenched streams, denoted by higher values, represent streams that are more regularly connected to the surrounding land. Translates to they would likely flood more. And the entrenched streams, denoted by the lower numbers, represent streams that are more incised and confined with less connection to the adjacent land. And finally, we'll briefly look at a few other ratios that are related to the planform of the river rather than its cross-section. Some of these, like sinuosity, which is the distance measured along the channel against the distance along the valley center, or slope, which is the change in elevation between 2 points against the distance between those 2 points along the channel, we've talked about in other videos. I'll link those in the description in case you're in need of a refresher. Meander wavelength is one we haven't talked about yet, but it's a metric that compares the wavelength between meander bends, often denoted by the lowercase Greek letter lambda, against the width of the channel. Established relationships typically put this ratio between wavelengths 10 to 14 times greater than the channel width. This can be controlled by the substrate under the channel, the steepness of the channel, or altered by humans, so those ranges are more of a natural standard than an all-encompassing one. And the last ratio we'll talk about, the radius of curvature, looks at the ratio between the radius of the meander bend, estimated usually by fitting a circle to the inside of that bend, against the width of the channel. We use this to estimate the potential for energy loss within the meander bend, where high values signify wide, sweeping bends that don't really lead to significant energy loss, and low values signify tight bends, where flow separation and turbulence within the bend leads to greater energy loss. So there you have it. Those are some of the primary ratios used in fluvial geomorphology. Now, there are many, many more that allow us to describe what we call morphometrics, which is the measurement of various forms or features in geomorphology. But you must be asking yourself, so what? Who cares about these, and what can we use them for in a practical sense, other than just to compare one river to another? Well, ratios like the one we've talked about are often used in river classification efforts, and those are often used to inform restoration of streams and river systems. Now, I mentioned the Rosgen classification method earlier. Here we see an example of 4 of the different ratios we discussed being employed to characterize the activity or potential for activity within a river by its morphometrics and its ratios. Of course, the Rosgen scheme is one of many different efforts to characterize how a river may behave based on its morphometrics. And in fact, if you're interested in learning more about river classification and the ratios or measurements used to do so, this paper in the Open Access Journal PLOS One by Kasprak and others from 2016 is a really great place to start, as it explains, compares, and contrasts some of the most prominent river classification methods used today, and what we can really infer with those methods and what those ratios might mean. So today we talked about some of the ratios we use in fluvial geomorphology, how to calculate them, and a bit about how they may be applied to river classification schemes. As always, I have provided links or citations to all reference materials in the description below. I hope you enjoyed the video, and I hope that you have a wonderful day. Thank you.